The image depicts Faraday's experiment 1. A fundamental demonstration of electromagnetic induction. Let's break down the image and the concepts it illustrates. Image components. Top section shows a sequence of 4 scenarios with a coil of wire, solenoid, connected to a galvanometer, G, and a bar magnet with its north, N, and south, S poles. The magnet is being moved relative to the coil. Bottom section. It's a magnified view of the coil and magnet, highlighting the magnetic field lines, blue lines, created by the magnet. It also includes text explaining the core principle. Explanation. 1. Basic setup. The experiment involves a coil of wire, a magnet, and a galvanometer. The galvanometer is a device that detects small electric currents. There is no battery in the circuit, meaning there is no initial source of voltage or current. 2. Moving magnet induces current. The key observation is that when the magnet is moved relative to the coil, the galvanometer deflects, indicating that an electric current is induced in the coil. This is the fundamental principle of electromagnetic induction. A changing magnetic field linked with a coil induces an electromotive force, EMF, which drives current. 3. Magnetic flux change. The text in the image explains that the magnetic flux linked with the coil changes when the magnet moves. Magnetic flux is a measure of the amount of magnetic field lines passing through a given area. In this case, the coil's area. When the magnet moves, the number of field lines passing through the coil changes, hence the flux changes. 4. Relative motion is crucial. The experiment emphasizes that relative motion between the coil and the magnet is essential. It doesn't matter if the magnet moves, the coil moves, or both move, as long as there is a change in the magnetic flux linked with the coil. 5. Induced polarities and current direction. The image also implies that the direction of the induced current depends on the direction of the magnet's motion and the polarity of the magnet, N or S pole facing the coil. This is indicated by the changing direction of the galvanometer's deflection. 6. Induced current only during change. The image notes that the induced current, EMF, is available only as long as there is relative motion between the coil and the magnet. When the magnet stops moving, the current disappears. Key observations to make, as listed in the image. Relative motion. Observe how the galvanometer deflects only when there is movement between the magnet and the coil. Induced polarities. Note that the direction of deflection indicates the direction of current and suggests that the coil itself momentarily acts like a magnet with induced north and south poles. Current direction. The direction of deflection shows the direction of the induced current. Induced current duration. The current flows only while the magnetic field linking the coil is changing. In essence, Faraday's experiment 1 demonstrates that a changing magnetic field can create an electric current. This principle is the foundation of many electrical devices we use today, such as generators and transformers.